Hey guys, today's video is going to work through a problem from the third page of the AP Chemistry summer review packet covering the mole and stoichiometry. Now this problem is going to go over some of the basics as far as molar mass. We'll work our way through simple kind of one-step conversions through determining what the limiting reactant is, all the way through products formation and percent yield. So again, this problem kind of runs the gamut of everything you're kind of expected to know coming into AP Chemistry. Should this video not be enough guidance, please feel free to contact me and I can walk you through some additional examples, or I can direct you through a plethora of resources that vary in complexity and kind of get you to where you ultimately need to be. All right, so let's jump right in. Again, this problem is nicely scaffolded. It says, fill in the missing pieces of information for the combustion of 2-propanol. You'll be happy to know that organic chemistry is not officially part of the AP curriculum, though we do use organic molecules quite a bit throughout the course of the year. So a simple combustion problem where we are taking our organic molecule, reacting it in the presence of oxygen to form both carbon dioxide and water. Given that we're going to be dealing with the mathematics of this chemical reaction, I think it'd be of value to obviously balance this equation first and foremost. So for combustion reactions, recall that the strategy is CHO. It's nice to balance the equation with those elements in mind in that specific order. So attending to the reactant side of things, I find that I have 3 atoms of carbon, I have 8 atoms of hydrogen, 7 there, and then the additional 1 coming off the hydroxyl group, and then 2 oxygens. 3 oxygens, as it were. Again, 2 here and 1 there. On the product side of things, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. So again, I'm just going to attend to these elements kind of straight down the line. Looks like I'm going to stick a 3 here first in order to get carbon up to 3, but in doing so, 3 times 2 is 6, plus the 1 additional oxygen is going to bring me to 7 oxygens currently. I'll then look to balance the hydrogen by sticking a 4 here. 4 times 2 gets me up to 8, so I can kind of check that off as well. But now I have 4 oxygens plus the additional 6 from the carbon dioxide there, so that gets me to 10 oxygens. Leaving this alone, right? I don't want to put any numbers here because I'm going to mess with the carbon and the hydrogen at that point, which I just got done fixing. The only place I can really put a coefficient is right here. Well, given that I need to get to 10 oxygens on the reactant side of things, I already have 1 embedded within the 2-propanol. So what I really need to do is to somehow bring this up to 9, which means a 4.5 is going to right here. 4.5 times by 2 gets me to 9, plus the 1, that brings me to 10. However, we can't really have 4.5 molecules of oxygen reacting. That doesn't quite make sense to have half of a molecule reacting. So instead, we multiply all of our coefficients through by 2. And as a result, our overall balanced equation is going to have coefficients of 2, 9, 6, and 8. Now that we have our balanced equation in hand, the first thing I want to do is figure out the moles provided, right? That's going to be our first step. I've been given grams, and again, grams tells me how much I have of something, but moles tells me the actual quantity, and those things are a little bit different, right? And it's the moles that we need to work with because that's what these coefficients are. They're molar coefficients. They specifically tell me that 2 molecules of 2-propanol are going to react with 2 molecules of molecular oxygen to form 6 of carbon dioxide and 8 of water. Okay, so we need to be dealing with things on a quantity basis. So for that first step, the strategy I'm going to employ is to use the molar mass, okay, of the specific molecules in order to convert grams to moles for each of our reactants. That's the first thing I'm going to do, okay? And so in doing so, what I'm going to start with is actually determining the molar mass for my 2-propanol there. So again, I have my carbon, I have my hydrogen, and I have my oxygen. I have 3 carbons, I have 8 hydrogens, and I have 1 oxygen. I'll multiply that number of atoms within this molecule by their respective individual like atomic masses that I'm getting directly off the periodic table that I've included with your summer review materials. This is going to be 12.01, this is 1.008, and this is 16.00. I do some quick multiplication, I arrive at 36.03, 8.064, and 16. Okay, so again, what these are the like the masses of these individual elements. I'll combine them together, and what I've solved for is again the molar mass. This tells me that I have 60.094 grams if I have exactly 1 mole of that molecule. Okay, now again, 1 mole, 6.02 times 10 to the 23rd, that's a really large number of that molecule. I would have that much mass on hand if I had that specific number of molecules. Okay, so now that I have the molar mass in hand, I'll use a ratio, right? We're going to use a lot of proportions in this video to talk about kind of relationships and to convert between things. So I'm given 18 grams of the 2-propanol, so the C3H7OH. I'm trying to figure out how many moles that actually is. And I know that if I have 60.094 grams of that same molecule, that is going to be equivalent to 1 mole. Again, that's what the molar mass actually tells me. It is how many grams per 1 mole. Normally, we just don't write that as far as our units go. We don't write grams per 1 mole. We just say grams per mole, and it's implied. So now that I have this proportion in hand, I can basically cross multiply, and I get 60.094 times by x is equal to 18 times by 1, and x is going to be equal to 0.2995. And again, that is moles of the C3H9OH that I've solved for. Okay, so that's the first step, is to take the grams provided, which again is how much, right? We would mass that out using like a balance or scale in the back of the classroom, in our lab setting. But this is the actual quantity. This is indicative of essentially how many molecules that are present, okay? The same thing for oxygen. I want to figure out the number of moles. I'm not going to walk through how to solve for the molar mass. The molar mass of oxygen is 32 grams per mole. So I'll go straight away into the conversion. So I'm provided with 500 grams. I'm trying to figure out, how many moles that actually correlates to. So some X moles of oxygen. And this is going to be equal, again, to our 32 grams of O2 over 1 mole of O2. And you might be wondering, where am I getting this 32 grams? Again, oxygen is diatomic. It's one of our 7 diatomic elements. So we're not using the 16 off the periodic table. We'll be doubling that and working with 32. So again, I cross multiply, and I solve for my number of moles of oxygen as being equal to 15.625 mole O2. Okay, so now that I have kind of these values in hand here and here, let's go ahead and update kind of our table just to kind of keep things nice and neat and organized. All right, so kind of that first step, I've solved for the moles provided. The next thing I want to do is figure out, okay, well, how many moles actually react, right? And the way that I'm going to do that is to compare the moles provided for each reactant to each other using the molar coefficients in the balanced equation, okay? And what this is really going to allow me to do is to figure out what is limiting and what is in excess. And so this first question we want to attend to is, we just got done solving for 15.625 moles of oxygen. Well, how much of that 2-propanol is actually going to be required to react with that amount of moles of oxygen? And this just involves some simple mole ratios, again, going back to our balanced equation. So it might be useful to kind of have that on hand, okay? So I know that per my balanced equation, I need 9 moles of oxygen per every 2 moles of the 2-propanol, That's our mole ratio. And I've gotten these numbers from the coefficients in our balanced equation, okay? And again, this is kind of like what happens per the reaction. Well, I'm told that I actually have 15.625 moles of that oxygen in hand. So I'm just trying to figure out, well, okay, if I want to react literally all of this oxygen, how many moles, so some X number of moles of the 2-propanol am I going to need? So I cross multiply, I solve for X, and I find that I have 3.47 moles of C3H7OH, okay? That's how many moles of the 2-propanol would be required if I wanted to react all of the oxygen. And so the question is, do I have this amount of C3H7OH? And the answer is no. No, I do not. In the very first step, I solved for only 0.2995. I have significantly less than what would be required, okay? So the answer is no. No, I do not. And what this means, what this tells us, is that the C3H7OH is our LR, okay? Which again, is our limiting reactant. That's the quantity that's going to dictate how much product I can actually form, okay? So again, the reason behind this is because if I want to react all of the oxygen, I'm going to require more of the 2-propanol than what I have, okay? So this first step is good, right? It tells me what the limiting reactant is, and then by default, our oxygen is obviously going to be our excess reactant, but it doesn't really tell me, how much of the oxygen, the excess reactant, am I actually going to need, okay? So again, I'll use molar coefficients from our balanced equation. I'll use the mole ratio, and I'll figure this out. I'm going to switch my ratio around. It doesn't really matter. But normally, like what I'm solving for, I like to keep in my numerator, which again, doesn't really matter. So I have a 2 to 9 relationship as far as the moles in our balanced equation. So knowing that this is the limiting reactant, knowing that this is the one that's going to run out first, I want to exhaust this, right? I want all of this that is available to react. And subsequently, I want to be able to figure out, well, okay, knowing that this is going to run out first, how much of the oxygen am I actually going to need? So again, I use that 2 to 9 mole ratio. I solve for my proportion, and I get 1.348 mole of O2, okay? So assuming that all of this reacts, how much is required of the oxygen? Is this amount right here, okay? The 1.348 moles of O2. And so do I have this amount of oxygen? And the answer is yes. Yes, I do. If you go back to what we were talking about earlier, you actually have 15.625. You have significantly more moles of oxygen than what you would need in order to completely combust with that 2-propanol. Okay, so again, the answer is yes. And basically what this tells us is that O2 will be in excess. Okay, let's go back and kind of fill out our grid. So as far as moles that react, we just got done saying that if this is our limiting reactant, so maybe I'll mark that, and then our oxygen is the one that's going to be in excess. The limiting reactant, as much as provided, as much as you have, all of that's going to react. Always, always, always. Okay, so 0.2995. Again, we just got done saying that if all of this reacts, we're actually only going to need or require 1.348 moles of our oxygen there. As far as step 3 goes, the moles that are in excess, well, you basically take the moles that are provided and you subtract from it the moles that react, which means the limiting reactant is always going to have 0 in excess. To figure out the amount of moles of excess here, we simply take the 15.625, subtract from it the 1.348, and we arrive at 14.277 moles of oxygen, okay? Significant amount of moles in excess. So moving on to step 4, we want to figure out the moles that are produced. As far as the moles produced, the strategy is that we want to convert moles of reactant to moles of product, right? We know how much reactant we have using kind of our recipe, which is the balanced equation. we can figure out the moles of product. To do that, we can use any of the reactants. It doesn't matter whether we use the 2-propanol or whether we use the oxygen, but we have to use the moles react, right? We cannot use the moles provided, okay? So again, we have to be talking about these values here, the moles that react, and you can use either one of these. It doesn't really matter, okay? You also have to use the appropriate coefficients. You have to use your balanced equation to set up the, the appropriate mole ratios. So let's go back to our problem. So again, you have to use the moles react, not the moles provided. You'd run into problems with using the moles provided of the oxygen because you'd be using a lot of oxygen and you don't actually have enough 2-propanol to react. Okay, and like I said, the proper molar coefficients. So let's say I want to figure out the carbon dioxide here. If we go back to our balanced equation, to solve for carbon dioxide, let's say I want to use our 2-propanol, okay? Well, I know that per that balanced equation, it was a 2 mole of the C3H7OH, the 2-propanol, to a 6 mole ratio. And again, these are the coefficients in our balanced equation. Well, as far as the moles that actually react goes, I found that only 0.2995 moles of that ethanol, 2-propanol, react. So I'm just trying to figure out, well, if I had this much in hand, and I know that it's a 2-to-6 ratio, essentially I'm scaling things up by a factor of 3, I want to solve for how many moles of carbon dioxide I can form. So I perform the operation, I find that I have 0.8985 moles of carbon dioxide. So again, I use the relationship between our 2-propanol and the carbon dioxide, knowing that whenever 2 moles of this react, I can form 6 moles of carbon dioxide. This is how much I actually have available to react, so I can solve for moles of carbon dioxide. In solving for oxygen, I can do the same thing. Just for good measure, let's go ahead and use the other reactant. Okay, so let's say that I actually want to start with our oxygen. Well, I know that is a 9 mole ratio of oxygen, again, per the balanced equation, to the 8 mole ratio of the water. As far as the moles of oxygen that react, that's only our 1.348. We determined that. Again, moles of oxygen. So I'm just trying to figure out the moles of water at this point. So I look to solve for X, and I get 1.198 mole of H2O. Let's go ahead and update our chart, again, for kind of good measure. So I have my moles produced now, which is our theoretical yield. This is assuming that we have 100% reactant to product conversion, which we'll get into here in a moment. That is the quantity of both reactants, respectively, that I'm going to look to form. So in the last step, this is going to seem very familiar. I want to figure out the grams produced, right? I want to know at the end of this reaction, what is the mass of these products that I'm going to have in hand. So to do that, it's very similar to the first step. I'm going to use the molar masses now to convert moles to grams, okay? The molar mass of carbon dioxide is going to be 44.01 grams, again, of CO2 per 1 mole of CO2. I'm going to set this equal to some X number of grams, right? That's what I'm looking to solve for. And I know as far as moles in hand goes, 0.8985. That's how many moles of carbon dioxide I just got done determining that I actually form. So straight away, I'm going to expect a mass that's less than 44, because if 44 grams, constitutes 1 mole, and I have less than 1 mole, I should expect to have an answer less than 44. And performing the math, I get 39.54 grams of carbon dioxide that are ultimately produced. Okay, I'm going to do the same thing for water. At some point, water is probably just going to be a molar mass that, because you've looked it up or solved for it so many times, you'll probably end up committing it to memory. 18.016 grams of water per 1 mole of water. Again, that is the molar mass. Trying to figure out how many grams of water are going to be produced. I had previously solved for 1.198 moles of water that get produced. So again, I cross multiply, solve for x, and I get 21.58 grams of H2O. Okay, so again, this is the mass of our products that are ultimately formed. So I can go ahead and again, kind of update our little graph here, our little chart rather, 39.54 and 21.58. Okay, so this top portion is now done. I've successfully converted between grams of reactants to grams of product. And again, this is kind of a full-fledged, stoichiometry, limiting reactant type problem, where again, I first converted grams to moles. Comparing moles of reactants to each other, I determined what would be an excess and what would be limiting. I then used the moles that actually reacted to determine the moles that are produced. And then in the final step, converted moles produced to grams produced, okay? This very last step of the problem asks me a question about theoretical yield and actual yield and how that kind of relates to percent yield. So it says, now imagine that upon completion of the reaction, you find that you only have 18.55 grams of water. Okay, so you run the reaction, maybe in some closed container, and we only get 18.5 grams of water that are formed. It's asking what is the percent yield. And this is a pretty straightforward one-step problem. The equation is that the percent yield is going to equal our actual yields, what we're able to kind of garner from the lab setting, over the theoretical yield. What are we supposed to get in an ideal situation? And we'll multiply that by 100 in order to get a percentage. So I found that our actual yield was 18.5 grams. I will take that and I will divide it by what that theoretical yield for the water was supposed to be, which was the 21.58 grams. I'll multiply this by 100, and I will end up getting 85.73%. So again, this is my percent yield. And this is a common problem. It's also pretty common to, say, solve for the theoretical yield, be told that your percentage yield is some percent, and to actually solve for the actual yield. That's also pretty common that you're going to encounter within this review packet. Okay? I hope this was helpful, guys. Have a great one. Thanks.